Ch4 Motion in 2 dimensions. We just learned about vectors and the coordinates. Say for example, this is initial position vector of OI. That's final position vector of OF, or we use RI or RF. We learned that a vector can be expressed mathematically by its x, y, and z position. So initial vector R of I is xi of I plus yi of j plus zi of k, simply ijk are the unit vectors, and xi, yi, zi are the position for this initial. And similar for the final position, we can use of x a final, y a final, z final, combined with ijk to express it. Well, if initially the particle is here and finally particle arrives there, it might experience something complicated starting from here and up there. However, if we ask the question of displacement, then that is initial point to the final. So this is where we start. After displacement, that's where we end. So this is the change of position. Delta R is the notation for change of position 3-dimensionally. Well, even though this is a 2-dimensional diagram, but delta R can be 3-dimensional because enter ijk express. So again, change of position defined as final position minus initial position. So in our case, if we consider this is 3-dimensional, then this final has this ijk turn, initial has ijk turn, as we learned how to do minors of two vectors subtract each other, that is ii turn subtract each other. So actually that comes out as x of final minus x of initial of I plus y of final minus y of initial of j plus z of final minus z of initial of k. That is the change of position. For 2-dimensional average velocity, we learned about velocity average. Before it's delta x over delta t, that's for 1-dimensional. Now it's change of position over time. That change of position is delta r. And for instantaneous velocity, before it's dx dt, now it's dr dt. Let's take a look at this case. R is a position vector of any kind. So it is I of I. This is just a position. So it's x of, it's arbitrary. X, y, and z of k. So if you d dt of this r, actually we have to d dt of 3 turns. We know that if we would want a differential of the 3 turns, then we have to take differential the first one, second one, third one. So what we have from here is dx of dt of I. That's first term. Second term, dy of dt of j. The third term is dz dt of k. If you remember, if dx dt we define as vx, then we have a reason to name dy dt as vy. Then we have a reason this is vz. This simply tells us a 3-dimensional velocity can be expressed as vx of I, vy of j, vz of k. Still, it has 3 unit vectors involved, ijk. Vx is x directions velocity, and vy and vz are y and z direction. I still like to add a vector for vx and vy, vz, because even though this is x direction, it still has a choice of to the right, to the left. So your vx could be positive or negative. Vy and vz are similar. So you can imagine when we describe an acceleration, we will also involves ijk for three-dimensional acceleration. Let's take a look. Acceleration instantaneous defined as dv dt. Now it has a meaning of three-dimensional v, three-dimensional a. So if we go back to define v, it's dr dt. That's three-dimensional position, change of position over time. That gives us v. We have this dr equals to v dt. And here dv equals to a dt. If that we have constant acceleration, if a is constant. Now remember, a is a vector, so which means the magnitude and direction both are constant. Then if we do integral dv, then a comes out and dt. So we will get that v final equals to v initial plus at. And from here, that this v is any v, we can plug in the v final. That is v initial plus at, vector, vector. And still have this dt. If we want to do integral, this will end up v initial t plus 1/2 at squared. Probably you will say, I know that. Well, let's take a look. V final equals to v initial plus at. If this is a three-dimensional case, what does that mean? Your v final actually is v final x of I plus v final y of j plus v final z of k, ijk for them. And initial is v initial of x of I, v initial y of j, v initial z of k. That's for the initial term. This is for the final term. They all have ijk. And your acceleration will be ax of I and ay of j, az of k, and have a t. Now what I'm doing, this is vector, 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 because even though you have initial of x, velocity you still can have a choice x direction to the right or to the left, so it still has a choice of positive, negative. Now let's take a look. If this is a vector ijk, right? ijk. And here, I term should add. So if I combine, what I get is v initial x plus ax. That is the I term, see? The two I term add together. But don't forget, this t go with this a, so the t is right here. Then we have our next term is v initial of y plus ayt of j, and then v of initial of z plus v plus a initial of z t of k term, right? If we combine I term, jj term, kk term. Now, it ends up that we have a vector on the left has ijk term, and the vector on the right also has ijk term. Two vectors are equal to each other. The I term has to equal to each other. J term equal, which means this has to equal to that, which is v final x must equals to that v initial x plus ax of t. So you can tell our next move is jj term must equal. So this must equals to that, the j term. So if we take a look at, this is a very good representation. This is x direction, end up like that. Then y and z should follow the example. What does that mean? That means even when we want to describe a three-dimensional case, we still describe the x direction, y direction, and z direction independently. Eventually, if we want to put together, fine. Final velocity, and x has something, y has something, z has something. And if we want to describe about acceleration, it has x, y, z. So I, j, k, x, y, z never mixed with each other. We have to separately consider the motion of x and y and z. But if the acceleration around x and y and z are all constants, then it follows the same motion equation of chapter 2. Let's look at a simple, very common motion, which is called projectile motion. Projectile motion usually is to be three-dimensional. However, if we follow the trajectories trace and then put the xy plane within that, then we can limit it to two-dimensional. So, say for example, we threw something at initial velocity of h meters above the ground at location of A. What's going to happen? As a matter of fact, if we have initial velocity like that, we can split it to v initial of x and v initial of y. Remember, any vector, this is two-dimensional, any vector can be expressed as, in this case, v initial is v initial of x, I, plus v initial of y and j. So it's two-dimensional. And then things x and y we have to consider separately. Let's look at x direction. X direction, if we ignore, if we say no air friction, and then the object has initial velocity called Vox. If there's no air friction, the object should keep a constant velocity. So x direction, the velocity simply keeps the constant. So we say VO, we should say V final of x always equals to V initial of x because velocity is a constant, no air friction. However, the issue of y direction is different. This is the VOY. If we only pay attention to the y direction, this is equivalent of we threw something up with VOY. We learn from chapter 2. If we threw something up, doesn't matter up or threw something down or just let go of it, because the G is always there. What's going to happen? This VOY is going to be decelerated because G is opposite direction of this VOY. So the object will slow down and reach the highest point, and then the G will accelerate it, so it will start to increase the velocity downward and eventually falling faster and faster. So, since this is a trajectory, the velocity should be tangential to it. If we draw this, it is very interesting that we can see the x component pretty much keep the same. Did you see that? See the lines? However, the y is different. This is how much y at B. There's no y component at C at all because this is the peak. VOY started with at the peak, VY equal to 0. And then it comes down, so the y direction start to increase. The y direction start to increase. The steeper the slope, the longer the y. So the y direction, you see initially it's up, then get shorter, slow down. No, which means y direction velocity just 0. And then change the direction, magnitude increase. But x direction keeps a constant because no air friction. Y direction, no air friction either, but there is a downward acceleration all the time. Let's look at this one. So the x direction, this is the v initial x, It is always same. So anytime Vx equals to that Vox, so we can simply say anytime of Vx equals to Vx of initial. How do we get Vx initial? Look at this relationship that Vx of initial simply is V of initial cosine of this angle theta. And obviously Vy of initial is V initial sine theta. But be very, very careful. It's not always that x component is times cosine, y times sine. Because right now the angle is with respect to x-axis. That's true. If the angle is with respect to vertical, then you have to look at diagram, x sine and cosine will be reversed. Now look at our y component. This is start with Vy initial, getting shorter, Vy get 0, change direction, get longer and longer. Now be very, very careful that if this starting from the ground, this is the point before it hits the ground, teeny little bit above ground. So did you see we still have the Vx initial same as before, and the Vy is very large. Should name. It's very interesting that this is the Vy of initial, and if we come back at the same level, the magnitude is same. We discussed that as a matter of fact in chapter 2. But this is a point before the impact, so your V final does not equal to 0. And what is it? We have to solve it. So be very, very careful when we solve the problem. We do not always get a V final as 0. And this next diagram also shows that this downward is the G. It is same all the time. It's going to cause the change of velocity.